When I give you a problem like this and ask you to determine the genotypes of a pedigree, you should always be asking yourself two questions. Is it sex-linked or autosomal? And then is it dominant or recessive? So I'm going to give you a couple hints that you can use to look for sex-linked patterns of inheritance and for recessive patterns of inheritance so you can figure out those questions. So for sex-linked, there's two different things that you can look for. One is that generally sex-linked patterns of inheritance simply have more squares filled in than circles, because the males tend to have the trait more commonly than females because it's on the X chromosome. So men only get one chance of getting an X chromosome, so they often end up with these traits more than females do. So you can't see that here. There aren't more squares than circles, so this probably isn't sex-linked. But a second thing to look for is, does a female always pass this on to her sons if she has it? So in this case, a female has it, she doesn't have any sons, so we can't tell. Here a female has it, she does have a son, and he doesn't have it, so this probably is not sex-linked. So if it doesn't have one of those two things, we're going to call it autosomal. And then to tell between dominant or recessive, we're going to look for the trait of recessiveness. And what we're going to look for in recessive genes is when a characteristic tends to skip a generation. So for example, here we have someone that has this trait, their daughter does not have the trait, but the son of that woman does have the trait. So it's skipped this generation. So this is a really good sign that this is recessive. So let's take a look at a couple other examples and see if you can figure out whether this would be an example of sex-linked or autosomal, and then dominant or recessive. So this first one, take just a moment, pause it if you need to. You should be able to see that this is sex-linked. The way you can tell is there are more males that have it than females. That's always going to be a sign for sex-linked. And then we're going to try and figure out, is it dominant or recessive? And in this case, we can see that it skips a generation. So this dad has it. None of his kids do. His daughter's a carrier, but she doesn't have it. So neither of these parents have it, and then it comes back in this generation. So this is really good indication this is sex-linked and recessive. Take a look at one more. You should have been able to say this is not sex-linked. There's no evidence of that. Here's a female that has it. All her sons do not have it. Here's a female that has it. All her sons don't have it. There's not more squares filled in than circles. So this is not sex-linked, so we're going to call it autosomal. Is it dominant or recessive? Well, does it skip a generation anywhere? No evidence of that. So we're going to say that this is autosomal and dominant. Here are the questions from the actual practice problems. If you have not yet tried these, please try them on your own and then check your work using this video. So the first questions have to do with the relationship between these individuals. So hopefully you can see from this, here's parents, that makes these two sisters. These are their parents, and the parents of each one of these individuals, that would make 1, 2, 3, 4 the grandparents. 5, 6, and 7 would be aunts and uncles, and of course, like I said, 11 and 12 are sisters. Notice 11 has a widow's peak, which is this hairline that comes to a point on her forehead, and her sister has no widow's peak. This is called a straight line. And so now we're going to try and figure out, is it sex-linked and is it dominant or recessive? So there's no evidence from our pedigree of sex-linked, and we can tell that it is dominant because it does not skip a generation. So having a widow's peak is dominant, not having a widow's peak is recessive. So now we can easily put on genotypes for these individuals. So anyone that does not have a widow's peak must have 2 copies of the recessive allele. So we can put on little w's for each one of those individuals. Everyone that has a widow's peak we know has at least 1 copy of the dominant allele, but we're not sure about the other allele. So to figure out the second allele, we have to be able to look at their offspring or their parents. So for person number 1, he has some kids here. 2 of his kids are homozygous recessive. So that means he must be heterozygous because somehow these children both got little w's from each parent. So he must have a little w to give in addition to his big W. Take a look at number 4. She's the same way. She has a child that has 2 copies of the little w gene. That means she must have a little w to give. She's heterozygous. Number 5 doesn't have any offspring, so how can we figure out if she is homozygous dominant or heterozygous? Well, we look at her parents and notice her mom only has little w's to give. That means she must be a heterozygote. This son from the same mom is the same way. He's got to be heterozygous because his mom only had little w's to give. Number 9 is similarly the same way, but because of her father, he only has little w's to give, so she's got to be heterozygous. Number 11 is probably the most interesting person on here in terms of genotype because her parents are heterozygote. Both of them. So we know she has at least one big W, but did it come from dad or did it come from mom or did it come from both? We're not sure. So we have to say that she is either big W, or big W, little w. Without additional information, we can't tell. So we have to say big W question mark. We're not sure what that second allele is. Let's look at the second example from hypercholesterolemia. So once again, is this sex-linked, and then is it dominant or recessive? Well, there's no pattern of it being sex-linked, and as far as skipping a generation, there's nowhere on here that it seems to skip a generation. It's in the grandparent generation, in the parent generation, and in the children generation. So we're going to say this is autosomal and dominant. That means that anyone that does not have this disease must be recessive. So we can go through and put their genotype on. Since this is hypercholesterolemia, we'll use little h for all of these individuals. What about anyone that has hypercholesterolemia? Well, they have at least one copy of the dominant allele, but we're not sure about their second one until we look at their offspring. So person number 1, does he have any offspring that are homozygous recessive? He sure does. That means he's got to be a heterozygote. He must have both a big H that he can give to some of his kids and a little h that he gave to some of his kids. How about person number 3? Well, person number 3 has a mom that only has little h's to give and also has a son that only has little h's. So we know person 3 has to be a heterozygote. Person 7 doesn't have any offspring, but once again, person 7's mom only has little h's to give, so she has to be heterozygote. Number 10 has kids that are homozygous recessive and a mom that is homozygous recessive. That means she's got to be a heterozygote. Person 11 has, once again, a mom that's homozygous recessive, so has to be heterozygote. Person 16 and 18 both have a dad that is homozygous recessive, so they must have gotten a little h from him, so they also have to be heterozygotes. The next problem had to do with cystic fibrosis. So once again, any evidence of being sex-linked. There aren't more squares filled in than circles. There are indications of places where a female has it, but she didn't give it to her son. So this is not sex-linked. Now we're looking for, is it dominant or recessive? Can we find anywhere that it skips a generation? Right here is a good place to look because parents have it. Neither of these children have it, but then grandchildren have it. It's skipped this generation. This is really strong evidence that this is a autosomal recessive disorder. So now we go through anyone that has the trait, since it's recessive, now those people are the homozygous recessive individuals, so we can put their genes on. Anyone that doesn't have it has at least one copy of the dominant allele, so we know they're big N something, and we've got to use their offspring to figure out what that other thing is. So for person number 2, they have 3 kids and none of their kids have it. So does that mean for sure they're homozygous dominant? Well, actually, no. It just means they have at least one copy of that dominant allele, but they might have gotten lucky and given that normal gene to all of their kids. We're not sure. How about person number 3? Well, this man has kids that have cystic fibrosis. That means he has a daughter, this is his daughter, that has cystic fibrosis. That means he must have given her one of these genes, so he must be a carrier. Big N, little n. Down on this line, we know each of these individuals does not have cystic fibrosis, but they have a dad that does, so they must all be heterozygote. Similarly, for 9 and 12, neither of these people have it, but they have a mom that has cystic fibrosis, so they must be carriers. Down to number 14, similar pattern. Mom has it, dad doesn't, 14 doesn't, so has to be heterozygote. Here we have, once again, the very interesting scenario of having 2 heterozygous parents. That means these individuals could have inherited a big N gene from one parent or both parents. So we're going to call them big N question mark and big N question mark. We're not sure if they have big N or if they have big N little n, but we know they don't have the disease. We're on to our last example here. This pedigree does have some indication that it is sex-linked. So once again, we're looking for more squares filled in than circles, so we can see that. And then now let's check the females. When a female has it, does every one of her sons have it? Yep, that's true there. It's also true here. So this is strong evidence of being sex-linked. Now let's look and see if it's dominant or recessive. Can we find anywhere it has skipped a generation? We sure can. Here is a woman that has it. Her daughter doesn't, but that girl's son does have it. So it skipped this generation and showed up in this generation. So this is a sex-linked and recessive disorder. This is muscular dystrophy. That means that anyone that does not have muscular dystrophy must have two copies of, anyone that has muscular dystrophy must have two copies of the recessive trait. So we go through and we put on the fact that they have two copies of that allele, except wait, this is sex-linked. So we have to list the chromosomes and the alleles. And remember, this allele is only going to show up on the X chromosome. So here's a female, so she's XX, and she has muscular dystrophy, so she has two copies of the recessive allele. Next up we have a male, so he's going to be XY, and he has muscular dystrophy, so he's going to have just one copy of that recessive allele on his X chromosome. A male with muscular dystrophy, again, is going to be X little dy. A female, X little d, X little d. A male, X little dy. A male, X little dy. A female, X little d, X little d. And a male, X little dy. Now we're going to go through those that don't have muscular dystrophy. What do we know? Well, we know they have at least one copy of the dominant allele, but we're not sure about the other unless they're males, like this guy, because he only gets one copy of this gene on his one X chromosome. So he is X big D, Y for sure. This male, same way. He's got to be X big DY because he only gets one chance of getting that big D gene on his one X chromosome. How about this woman? Well, she's X big D X, and what about that second thing? Well, we know that she gave her X chromosome to her son because the dad gave the Y chromosome to this boy, or else he wouldn't be a boy. So we know that this woman has to be X big D X little d, otherwise she couldn't have given this little d to her son. How about this woman? Well, we know this woman doesn't have any kids, so we've got to look back at her parents, and when we look at her parents, we see that her mom only had little d genes to give on her X chromosomes. Since this woman definitely got one of those X chromosomes, she's got to be X little d, X big D. Down to these last three kids. We can see what their parents have. We know none of them have muscular dystrophy, so they all must be X big D from someone. Well, where did they get their big D from? We know that this dad gave his big D, his X chromosome with big D gene on it, to his daughters for sure. What about their mom? Did she also give the big D gene on her X chromosome or not? Well, we're not sure. So for these two daughters, we have to just say they are X big D and then something else on their other X chromosome. That we know they have an X chromosome, but we're not sure which allele they have there. And this boy, well, we know for sure he got his mom's X big D chromosome because he got his Y chromosome from dad. So there you have it. If you have any questions, please check in with me. Thanks.